Good to be here. Good to be wearing my red coat, I want you to know. I made it special. Anyhow, what I want to do is talk about a new way of looking at estimation. I've been doing this basically since about 2007 when my colleague Moshe Idan spent a sabbatical 2 years actually with me, and this is the outgrowth of a dinner conversation. With me along is Nate Snyder, who is my last student. I've had 4 students in this area, and he's done a remarkable job not only on the theory and making the structure of this methodology more numerically simple, but basically his ability to work with computers has been enormous. When you get to be my age, you do less of that, less computer. I get to learn a lot more about how to do coding. I guess that's the big thing. So let me just basically talk about what I'm doing. Well, the beginning of this whole thing is talking about linear systems with inputs which are Gaussian noise. And that was a technique devised in the actually 1960s by Rudy Kalman, and that particular structure is based on Gaussians. It's analytic, it's recursive, and because it's Gaussian, it's the probability, the conditional probability, given the measurement sequence, is unimodal and symmetric. So it's very, very rigid. On the other hand, another recursive scheme and analytic, which I would like to emphasize, I don't know of many others that are like this, but this one is a linear system based on Cauchy distributions as inputs. They're heavy-tailed distributions, and these form a new way of looking at estimation. And when you look at the conditional probability density function for the with this Cauchy's as inputs, the conditional probability density function is neither unimodal, has many peaks, can have many peaks, and is not symmetric. So it's a far richer type of density function, and it really describes what usually goes on with most estimation problems. Gaussians are not that good. So let me tell you about the Cauchy and the class that the Cauchy is in. So the class that the Cauchy is in a class called symmetric alpha stable densities. Well, the point is, stability isn't dynamic stability. Stability has to do with the central limit theorem. So, for Gaussians, basically, this class means that sums of Gaussians are Gaussians. And if anything has a second moment, multiple sums of these things converge to Gaussians. But anything in this class except the Gaussian don't have finite variances. So they're all infinite variances. So the class is described actually by its characteristic function. Okay, that's what it, so what I have here is the characteristic function of a probability density function, which is basically the Fourier transform of that probability density function, of which there are only 3 analytic PDFs which basically match this structure. One of which is the Gaussian, the other is the Cauchy, and the other one is Levé. But basically, Levé, talking about Henri Levé, basically he came up with this structure a little bit deeper than what I have here. These are all nice and symmetric. But basically, this new over here is the spectral variable, and this is the characteristic function. And if you look at the density functions for the Gaussian and the Cauchy, so the density for the Gaussian is e to the minus x squared, as we have over here, And that gives it really, this is the dotted line for the Gaussian, very light tails. Whereas the Cauchy, which is something over a polynomial, a second order polynomial, you get tails which are much richer, which is this, if I could keep one in the same place. You have one here, which is the solid line, and you can see the tails are significantly larger than that of the Gaussian. And if you took the Fourier transform of this, you would find that this would be, alpha would be 2, so this would be nu squared, which is the characteristic function of a Gaussian. And if you take the characteristic function of a Cauchy, you would see that this is nu to the absolute power, okay, weighted by beta. In fact, this one over here is exactly, consistent with that for alpha equal to 1. But the point is that these two are in the same class, which are these alpha symmetric variables. Okay, so what is characteristic about this is that everything except 2, and I have here, actually the class goes from 0 to 2, but I didn't go any further than 1. So the point is they all have infinite variances. That's a kind of a strange thing to work with, especially if you want to do Monte Carlo results and see what the convergence is, because sometimes it won't converge. So you have to be careful about that. So, and there are no closed form solutions, but of the PDFs except the Cauchy and the Gaussian, and that's why we work with the Cauchy. It's analytic. Okay, and now what does it fit? Well, radar and sonar. One of the things I want to do is show that in clutter, basically, this scheme is fairly robust. Atmospheric turbulence, I want to show low Earth satellites, which are impinged by the fact that the density at these altitudes basically are very impulsive. And there's other things like adversarial motion and economic systems. I like to show you economic systems, but nobody works with me on this area, so you're going to have to work with aerospace type problems for this. Okay, so let me talk about the formulation of this. Again, this is just a linear system. This is in discrete time. WK and VK are basically the input noises to the system. Z is the measurement, X is the state, and they can be of general sizes here. I just want to emphasize that you'll see Y of K, which is the measurement history, because this is based upon the entire sequence. And even though WK and V of K are Cauchy distributed, but I'm having them here as vector. I'm going to only talk about them as scalars, but there's no problem. And some of the problems I'm talking about, generalize this, like the Earth orbiting problem uses GPS and uses 3 pseudo measurements at every instant of time. So it's not 1, it's 3. Okay, so for the state, so when we started this, we did the scalar problem. And we could generate analytically propagate the probability density conditional probability density function directly. But when we try to generalize it to the end state problem, it didn't generalize. And so we had to go to a different form. And the different form was basically, instead of the conditional PDF, we took the characteristic function of the conditional probability density function. And as my friend Carl Astrom said, one of my takeaways is, I've never seen a filter designed from characteristic functions. So I'm just relating that along. Okay, so given all of that, what I have on the other slide are the characterization of here we have an end state initial condition for each of the elements multiplied together. They're all assumed independent here. And then I take the characteristic function, they're basically a product of each of the individual characteristic functions, and I write it here as basically a sum of alpha operating on AI transpose on nu. So what I really write it as, but the AIs here are unit vectors. But in general, you're going to see this a lot, that A nu, a linear function operating on the spectral vector, is prolific within the structure. And what it does is it leads to a bunch of hyperplanes. And I'm going to talk about hyperplanes and the orientation of these hyperplanes to a set of, to basically a central arrangement of hyperplanes for which I'm looking at cells. And this plays an important role in the structure. Just like maybe in Gaussian theory we had Riccati equations, think of it that now we have these hyperplanes, and you're going to see more of that. And this is just another statement of the measurement noise, which I use gamma, and over here we have the process noise, where the normalization factor here is beta. Okay, so basically, what I want to do is talk about how we go about this. Well, from first principles. Okay, so we start out with what is the conditional probability density function? Well, the conditional probability density function of the state at time k, given the measurement sequence up to k, is basically, you could look at it as the joint density function of y of k and x of k divided by a normalization function y of k, which you know, because you know y, you know the measurement sequence. So what we do is, instead of generating this ratio here, we just generate the numerator, and the numerator, which is the joint density function, we're going to call the unnormalized conditional probability density function, which is f bar. So this is the guy we're really going to propagate. Well, not exactly. This guy can only be obtained recursively for the scalar problem, and so what we're going to do is we're going to generate the characteristic function phi bar, and that is what we're going to form recursively and in closed form. This is what we're going to generate. Okay, so remember, we're going to be looking at the characteristic function, and so what we're going to do is take the Fourier transform of that density function, which is what we have over here. So this is the density function at time k minus 1 for the state at k minus 1. Okay, we just processed a measurement. We're all done with that. Okay, and what I'm doing here is just taking this density function and just defining what I mean by the characteristic function, which is the Fourier transform, where this j over here is the imaginary number, and nu over here is the spectral vector, and so I'm just taking this transform. Now, in propagation, I'm going from time k minus 1 to time k. Okay, so using the Fourier transform, it's just a product, because in the state world, it's a convolution integral. So that's nice. We get this process over here. But now you want to make a measurement update at time k. So here we're at k minus 1, the measurement's up to k minus 1, but we propagated up to time k through this structure over here. Notice this is gamma transpose. Where the gamma is, that's where the process noise came in. Okay, so now we're over here, and we want to include a measurement. So this includes the measurement. See, zk over here is included in the measurement structure, but this is the convolution integral that we want to solve. Okay, it turns out this convolution integral we can solve in closed form. And that's what I want to show you, what it looks like, this convolution looks like in its closed form structure. Okay, and that's what the next slide is about. is what it looks like, and the next few slides characterize it. After I do this, I can start showing you pictures of applications, but I wanted to go through this and to give you sort of maybe some insights into how this thing actually works. So what we have here is the solution to the convolution integral. Okay, now that is equal to, I left it as a double sum. The reason I wanted it as a double sum here, and we can take that away, is that this sum is a bunch of parents. Okay, so at k minus 1, that means I'm at time k with the measurements up to k minus 1 only. Okay, I call this group of terms the parent. Now, each parent gives rise to a bunch of kids. Okay, and the kids are given by this summation over here. Okay, so what I want to do is be able to talk about how I go from the parents to the kids and what kind of a structure I use. But I want to do is give you some insight into what these functions look like. Now take this function over here. This is the exponential of a function y. Well, that y over here is given really by the absolute value of this linear function operating on nu. Okay, so again, here's where we get these hyperplanes from. Okay, now if you look at this guy over here, and then you translate down to g, you see that this guy in the denominator, when I integrate a function which is a linear function of nu, I'm going to get terms in the denominator. And so these terms in the denominator had come from here. Okay? Now these terms in the denominator, which is this g over here, GIM2, hey, those are signs of these linear functions. Okay? Signs of linear functions. Okay, so that's what I have over here. And not only that, these are all in the numerator. But what is this thing these are the things in the denominator. What are these things in the numerator? Those things in the numerator are the old g's of the parent. Okay? And how were they formed? They were formed in exactly the same way. You had a denominator. And its parents also had a denominator. And if you tunnel all the way back to the initial part, you get sums and sums of all these terms. So we got to get some way of doing that more, computed in effective way. And the way one looks at it is, well, you have these sine functions. So this guy over here is only a function of sine functions. If you take these linear terms, which are hyperplanes, and you look at these hyperplanes forming a central arrangement, it has a whole bunch of cells. In each of these cells, the g's are constant. Okay? The g's are constant in that cells. So in order to look at that in a proper way, it turns out that if you look at the integral formula, the child points to a particular cell. And the child points to the particular cell in this particular way. So if it's a first child, the first thing is this 1. Notice, on one side, where there's a plus sign over here, this guy over here is plus 1. And over here, the sign of 0 is made minus 1. Okay, so those are the differences of the structure. The definition of what you mean by 0 in this case. And these guys point to a cell of the parent. But what's beautiful about this is, if these cells point to a parent, then the parent has to have the cells of the child as well. So we use that in order to propagate the sign sequence of each of the hyperplanes and each of the cells. So we generate this table of pluses and minuses. This turned out to be like about 100 times faster than the way we were doing it before, which I thought was really clever. Okay, so let me just, before I go on and give you an example of this sequence, let me basically talk about some of the parameters that are in here. For example, this guy over here, B, which is over here in the exponential. This guy over here does contain the measurement in a linear way. So this guy over here, the C over here, because this is complex, this is the imaginary part, this also contains the measurement. And you can see, if it contains the measurement here, then this G contains the measurement in a very non-linear way. Okay? Things aren't that simple. So I just want to make the point here that a lot of the parameters basically can be computed themselves recursively. C and B are both functions of a measurement history. What I'm going to do in the future is I'm not going to use a double sum. I'm going to use one sum for all these terms. But notice that one of the problems, or the problem that we have, is the sums grow. Every time I make a measurement, you get more terms. So the question is, can you do something about stopping the growth? Okay, so, and another thing I wanted to bring out here is this exponential term over here. This is a term in the exponential. Basically, when I want to get the mean and the variance, I've got to differentiate the characteristic function. But isn't it interesting? The characteristic function looks really weird, right? It's got all these sine functions in there and absolute values. It turns out that you could prove that it's twice continuously differentiable. Okay, so you get a nice structure in there. That this term over here, not including the new, but all of this, is an n-dimensional structure which comes out of that differentiation. I just wanted to point that in. So the point is that hyperplanes form cells. In the cell, the G's are constant, and the cell is identified by a sign sequence associated with the hyperplanes. So what do the hyperplanes do? They divide, n-dimensional space into two parts. Okay, so the innovation in is the propagation of the enumeration table. So let me just draw a two-dimensional structure out so you get an idea of what's happening. So here we have three hyperplanes, A1, A2, A3. Plus is the plus for here, this plus over here is the plus side of this hyperplane. Minus is the minus part of this hyperplane. And the same thing is true for A2. We have a minus here and a plus, and for A3. And so what these things do is they structure the cells. So over here, I have the cell, which is now plus side of, it's the plus side of A1, the plus side of A2, the plus side of A3, so I get plus, 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 and that defines the hyperplane. Then if I go down here, I get minus, plus, plus, because the minus sign is associated with the minus sign of the A1 hyperplane. So as I go through all of these, I identify all the hyperplanes. So what I do is I can construct a table, and the table, the columns are associated with each hyperplane's sign sequence, and the rows are associated with each cell. So if I look at the top row, it's associated with the plus plus in red. And if I look at the next one, it's associated with the red minus plus plus, and so forth. And when I do that, I get a enumeration table. And this is the table that I want to propagate. All I'm doing is propagating plus or minus ones instead of doing, computation. Okay, so what I have next is I put a blue line here, which is gamma. I'm propagating over the dynamics and the process noise that's coming in, and so therefore I kind of split these cells over here, and so what I get is, instead of having 6 cells here, I have 8 cells here, and this sequence on the left-hand side is all due to, you see the blue line here, is plus, 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 blue, plus here. So this line over here is associated with the hyperplane gamma. So this is associated with A1, A2, A3, and gamma. So that forms the propagation. Okay, so the next one is, how are we going to do an update? So what we want to do is go to this, we reproduce the parent over here, and we want to get a sign sequence which are the same, except for the first child, it's going to be a plus or minus 1 difference. So we look at this structure over here, and we have a plus here and a minus here, and the 3 hyperplanes associated with the last 3 are the same, here and here. It's plus, 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 plus here, plus and minus. If you look down over here, that happens with a minus and plus with all the minuses. So for the first child, we put that over here. So that becomes the new child, which I can go from this child to the parent and get its G's. Because these cells here of the child are in the parent, and I can pull out those G's. And if you look at, that's the first child. If you look at this over here, the yellow is the second child, the blue is the third child, and the green is the fourth child. So you can do that and pull out, and this way, by this method, you can propagate the enumeration tables. Okay, so that's a simple way of viewing it. But then once you've done this, it's sort of interesting. You get a sequence over here, and these are identical. That means these 3 having identical sequences for those 3 hyperplanes must mean that those 3 hyperplanes are the same. So they co-align. And so I take those 3 away, and what I have is now the new child 1, which has this as its enumeration table. And then I go from there. And it turns out for 2-dimensional structures, boy, a lot of them generate down to 2 manifolds, as it turns out. Okay, so this kind of goes along with that, but the point I want to make is that what we're able to do is propagate these enumeration tables. Okay, so now what I would like to do is talk about how to get the conditional mean and the conditional variance, because I've now formed the underlying structure. Oh, one of the things I want to make before I go on to that is that when I'm able to do this and get these G's, it turns out that the exponential form, let me just put it over here, this piece over here, is common to a lot of terms, it turns out. And so therefore, the things that are different are the G's. But now that we have these G's, we can add them together with the same exponential form and reduce the number of terms. So the way we've been able to reduce terms is, number 1, combine terms. Second of all, it turns out that under sometimes this guy over here becomes extremely small and we can neglect it. Okay, I just want to say that we try as hard as we can, but no matter what, it turns out that you still have terms that keep on growing, and I want to talk about how we get rid of that term growth. That's the last thing we got to do. But on the way to doing that, let me just talk about the partial differentiation of phi to produce the conditional mean and the conditional variance. What's nice about this structure is all you got to do is differentiate it if it's differentiable. Well, it turns out it is twice differentiable, and that if you look at the G's and you take a value of nu, which is in a fixed direction, and you multiply it by epsilon in a particular cell, doesn't make a difference where you are, you pick that direction, you let it go to 0, in that cell, all the G's survive for those values. The thing that doesn't survive is the fact that that the exponential goes to 0, and so what you have left is basically this guy over here, which comes out of the differentiation. So if you differentiate it once, you're going to find that you get this for the mean. If you differentiate it twice, this guy, y bar, appears twice, and it's an n-dimensional vector. So when you do all this, you get the following. if you let epsilon go to 0 in the characteristic function, you reproduce the normalization factor. So you get it back. That's pretty cheap. Okay? So it's just the sum of the g's. When you take the first differential, which is over here, and you let epsilon go to 0, you get this y bar times g, and you divide by f, which is the normalization factor. And if you do the second moment, you need to get 2 of these y bars. Notice it's y bar transpose, weighted by g, and the normalization factor. What's interesting about this is you've got to be really careful about one thing. This has got to be real. Okay? This part over here got to be imaginary. Okay? And this part over here is got to be real again. Okay? So the numerics become important in how this thing is. And approximating any of these functions is not so simple because this characteristic has to come out of it. But anyhow, the conditional variance is basically just subtracting the second moment from the product of the conditional means, and we get the conditional variance. So we get a nice structure. Okay, what I want to do now is just do a simple problem, which is n-dimensional state. Just do one measurement and see what the mean and the variances look like. But the reason I have to do this is, one, it's instructive to see it. Number two, it's the basis of how we truncate things, because this is what we use in order to initialize a window of data. In other words, we take a finite length window of data in order to be able to truncate this growing sum. So how do we initialize it is kind of what's in here as well. Okay, so what we do is we have z1 is equal to hx plus v1. And what's important about this is that the normalization, you need, well, here's the important part. H is equal to h1 through hn. And I should have said it here, each of these h's are non-zero. Why do they got to be non-zero? Because this measurement has got to see every one of the values of the state. It's got to see it, okay? And it's got to be seen in terms of this one measurement. If I do that, okay, I can get this normalization factor. Okay, yeah, I can get the conditional mean, which is this vector over here. But what I can also get is the conditional variance, which is given by this matrix, which is positive, definite, and finite. Now what's happening, which is different than what a Kalman filter is, hey, all of the initial values have infinite variance. But these are density functions that have a glob of probability in the center. Okay, so when you tell it that you see a measurement which has got finite value for every one of the dimensions, it knows that basically it's not going to be infinite. And that's what it does over here. Now what we do with this thing over here, which I think is another innovation, is it turns out that I can initialize a window of data, by taking the last window's data. So it took, say 6 frames of data, and then I took the mean and variance, and then I used it to initialize another window. And it turns out that when I do that, all I've got to do in order to get the A's that I need in order to generate the characteristic function is to take a positive definite matrix, not exactly the variance with something added to it, and rotate it into a diagonal form and use that rotation, the rows of that rotation matrix as the new A's of the system to start off this process. So all I've got to do is generate a rotation matrix, which turns out to be pretty simple. Okay, so this is what we have over here. So this is the sliding window bank. And so we start here at time 0, effectively, and here's the measurements. Goes from 1 to 6. And at this point over here, I announce my mean and variance, say. Okay? Now, at the next step, I got to start that window. Well, I wait for this one, the second window, to start. And at this point over here, I start the second window ends and gives its mean and variance to this guy over here. This guy uses it by basically constructing a rotation matrix and using the rows of the rotation matrix for the new values of A over here, and then it starts a new one. So these windows continue on and on and on, and in this way we get a continuous structure for the estimator. This is the major approximation we have to make. As you get better computers, you get bigger windows, and if you get bigger windows, then you can put more data into it. I just mentioned term reduction is when you can add the G's together, and one of the things we've done is use GPUs in order to, because it lends itself to distributed computation. So let me just talk about what this thing does. So these are some pictures. So here we are at time 3. Okay, the green is the, where the arrow is, the green is the conditional probability density for the Gaussian, and the blue is the conditional probability for the Cauchy. Okay, and the red over here, this arrow over here, points to the actual state. Okay, this is in 2 dimensions. Okay, so what happens this is at 3. At 4, the way the dynamics work is that the state at 4 sees a process noise occur. Okay, a large process noise occur. Okay, now the filters don't know that, but what happens is, oh, the state moves over to here. Okay, but now these two guys see this measurement, the Kalman and the Cauchy see this measurement, and they're trying to figure out what this measurement means. It's a big jump. So the Gaussian is still this green line here. Okay? But the Cauchy has a bump over here and a bigger bump over here. So what is it saying? It says, I see something strange in the measurements. It could be process noise. If it's process noise, I can stay where I am. No, I'm sorry. If it's measurement noise, I can stay where I am. If it's process noise, oh, this should be a jump. And that's what it does. It jumps over to here. So you see a bump here and a bump here. So the Cauchy is wondering what's going on. The fortunate thing about the Kalman, it has no idea. So the next step is that the 2 bumps become about equal, and the real value is here. And then a little bit, the next step, well, the Cauchy has moved over here, and it's unimodal, not bimodal like it was before, but the Kalman filter just hasn't gotten the message yet. Okay, so this is our pitch. So let's look at some of the things that can go on. Here was an interesting thing that Nate showed. He took a second order system, a pendulum. It's got a small, it's got a nonlinearity in it. So I haven't really emphasized it, but most of what we do here is just like Kalman filters. We linearize around the best estimate of the state. So we do that here, but now what happens is, here we have a pendulum. It has an angle and an angle rate. Now, if you look at the first 40 seconds over here, you get these following lines. You get the green line and the blue line, or the green dotted line, and the blue solid line. Those are both, that's the tracking of the conditional mean for the Kalman filter and the Cauchy. And now this simulation is in Gaussian noise. Okay, so the Kalman filter is the best here. Okay, okay. So the dashed line over here, which is kind of purple, is the conditional variance of the Kalman filter, which is basically pretty much a priori known. The red line on top of this over here basically is the one sigma value that's generated in the Cauchy. And I forgot to show you that, that the covariance is a function of the measurements. The Kalman filter variance is a priori known. Okay, so what we're getting here is, and that was in the example, it was z squared. So you can see it hugs it pretty well over here. It's a little bit higher here for the angular rate, but it basically adapts to the noise that it sees. Then at 40, what we do is we multiply the damping by 4. So it's 4 times more damped than we thought it was. And so we see what happens at 40. How does the Kalman filter respond? Well, that's the dashed line over here. Okay, and then we see how the Cauchy, well, it dumps up a little bit, and then it goes back in. And it also jumps up pretty high here, and then it goes back in. So in the Gaussian environment, putting a parameter variation basically affects the Kalman filter far more than it does the Cauchy. So even though you have effective gain and phase margin associated with the Kalman filter, 60 degrees of phase margin. I'm not sure what it means and how to generate. So there's things to be done here. The other thing is we multiply it by, we changed the damping and we reduced it by 4 times. And here we see, again at 40, things are tracking pretty well. And then you see that the Kalman filter is oscillatory, but you also see an oscillatory structure in the Cauchy, but far lower amplitude for that. Okay, so let me just talk about another problem. This one I want to do is talk about robustness within the class of alpha stable systems. So here I'm going to be talking about radar clutter going from alpha equal to 2, which is Gaussian, to alpha equal to 1, which is Cauchy. And the work that was done by USC shows that, radar in clutter can be like alpha equal to 1.7 all the way up to 1.1. So we're not too far off here, but at least it illustrates its kind of robustness structure. So what we're talking about here is making a measurement of the line of sight angle is what our measurement is going to be of a radar system. And over here we're looking at y, which is the relative position in the transverse direction. We're looking at y, its velocity, the relative velocity, and the acceleration of the target as well. Okay, so that's what I kind of have over here is that, and this over here is a Gauss-Markov model that I have that you can represent for the Kalman filter because that's all you can do, but the actual acceleration really is a telegraph model which we put into the simulation, which has the same autocorrelation as the Gauss-Markov process. Actually, which doesn't do that badly, but they're 2 different processes. Which is what we use. But this is what we use the telegraph model in the simulation. The other part is, here's the measurement. It's an arctan. It has a nonlinearity. And the VC over here is the closing velocity. And so it gets really small as the time to go gets small. But the point really is this is a representation of the noise that are here. And here I took it out of Bryson and Ho and for Gaussian models. And R1 is like a fading noise. R2 is like a glint model. But what we do is we're going to represent this first as Gaussian, but then we're going to represent its structure. We're going to fit its structure basically to different values of alpha, all the way up to alpha equal to 1, starting at 2, going down to 1. That's what we're going to do. Okay. And the dynamic system is a continuous, because I can't handle the continuous systems, but we discretize it. And I think the sample rate is about 1/10 of a second. Just to give you an idea how it used to work, this is what we thought before we were processing it with these enumeration. So this is this is where we were. We were using, for example, Nate's computer was around 10 hertz, 11 hertz here, and using a V100, we were able to get speeds for this problem at 100 hertz. Now, I think we're down to about 1,000 hertz, and here we're probably up to 100 hertz. Okay, so we're going even faster. Okay, this was we thought it was a terrific way of doing it. It is. It's very insightful, but I will talk about it some other day. Anyhow, so this is the models we're using. I just want to show this is the measurement exactly, and over here we got a pulse, and this is the input telegraph model that we used. The thing I want to talk about here is only that we used different windows from 4 to 8, and it didn't seem to make much of a difference. So sometimes the windows don't have that much information, and you can get away with it. And it turns out that this is where the Kalman filter kind of lost it over here. So that was the only part of that. But what I want to talk about is how you could talk about robustness. So we had to do averaging. Okay, so averaging is a little difficult when you have infinite variance terms. So what did we do? So we do a Monte Carlo of 9,000, okay, for all the alphas. But what we do is we take the sum of the log of the error squared. We can't take the sum of the error squared. But the log actually is lower bounded by a linear function. So linear functions can just barely be integrated. In fact, maybe you might take that class out. But anything below it actually converges. And so what we do is we use the log of this divided by MC. So we take this is the data we collect over 9,000 trials. We raise it to an exponential form and take the square root. And it kind of gives us a kind of nice values for the 1 sigma for this geometric mean. And so that's what we have here. So the basic point is this is relative position, relative velocity, and acceleration. We don't do very well in acceleration, but basically most of what the noise is in measurements, and it's pretty noisy. So if you look at the bottom over here, this green solid line, you can see a little bit here. Well, that green solid line is in a Gaussian simulation. Okay? And then as you keep on increasing alpha, or lowering alpha to 1, and alpha to 1 over here, that's the Kalman filter. But if you look at the Cauchy, the blue line is really thin, indicating that over this class, it's very robust. So that's the point of this demonstration over here. Okay, so the other part of it, we talk about missile guidance, but we can talk about that later. The last thing I want to talk about is the low Earth orbit satellites. Here we do two things. We have a 3-state problem and a 2-state problem. The 3-state problem, we get a window of about 5, and 5 means 5 time steps. Each time step has 3 measurements. And the 2 one, we have 8 time steps, but 2 measurements at each step. Okay, so to get an idea of how the windowing affects this LEO problem. And you can see that it does affect it in subsets, but here is the 5-state problem. Let me just say, what are we estimating? We got 3 positions, 3 velocities, and density. And the density is the guy that is impulsive. Especially if you have bad weather on the sun, for example, lots of solar flares, you get a lot of fluctuation in the density on Earth. Okay, so that's another problem that we have to deal with is the sun's weather pattern. The thing is, I got this from Nasser Goddard. And basically, this was given to me by Russell Carpenter. And he analyzed the data that he had gotten off of these satellites. And he used the number of alpha is equal to 1.3 for the density, and beta is a scale value of 0.0013. And that basically means that you've got a pretty strong tail in the distribution, but the distribution is extremely narrow. It's got a very narrow structure. So that's what we're using here. Okay, so we fitted the Cauchy and the Gaussian. We made least squares fits, and I didn't change anything. And basically, what it's getting is GPS measurements with about a standard deviation of 2 meters. But here is what we got for the tracking of the density as we jumped it up like 700%. So you can see that the green line here is the Kalman filter, and the line over here is the tracking blue line of the Cauchy in doing that. And this was for the 5-state problem with a window of 8, and for the 7-state problem with a window of 5, it's pretty much similar, but it's a little bit off here, as you can see, and over here. So it's not tracking quite as well as that of the 5-state. But just to give you an idea of this is the 5-state problem, and I just want to give an idea of how this works, in the sense that the tracking over here of the Cauchy is pretty good and pretty smooth, and over here is the density tracking. Now what happens is the Kalman filter is doing pretty well, but then all of a sudden the jump occurs, and so yeah, the tracking for density was okay, but the tracking of position and velocity got really corrupted for the Kalman filter. Now look, you can tune the Kalman filter to track better, okay? We didn't do any tuning. We didn't do any tuning to the Cauchy. We didn't do any tuning to the Kalman filter. Now the point is that not only are you getting over here some idea of how the tracking will go, but you get some idea of what the variances are, because the Cauchy is adaptive to the noises it sees and gives reasonably good estimates of what the variance is. Maybe a little bit overbounded, as you can sometimes see. Okay, so this is for the 7-state problem, and basically the same thing happens between the Cauchy and the Gaussian. So my point is, hey, if you got a filter to use, well, try this one. Okay, so we're trying to do real problems for this underlining structure. So in conclusion, basically is, we've got another recursive closed form solution. Numerical insights have dramatically reduced the computation time for this, and robustness is basically seen in the 3 examples that I used. So, we're still in the business of trying to prove how robust this is from a theoretical point of view, but at least we've got some numerical direction in all this. And the last thing I would say is, to make people use this, that Nate has put this in a Python wrapper with his C code, and basically this could be available right now for Linux or Mac operating systems, and we're working to put this on Windows as well, and maybe use MATLAB instead of a Python wrapper to make people use it. So that's the theme. Done.